Hello everyone and welcome to the GUI section of the neural network. Today we'll do this in two steps. First, we'll train a very simple model to do classification of hand digits and handwritten digits, which looks something like this. So these are the handwritten digits that we can. These are the zeros. You have all the data from 0 to 9. And then the second part we'll do, I'll show you how to do the autoencoder on images. Basically, because there are a few things that you need to tweak in the neural network model to make it work. Okay, I'll split this into smaller parts. This would be our data preparation. This is our neural network model. This is how KNIME works. So you define your data preparation is separate like any other machine learning model. Your NN model is designed like this graph of nodes. And then you have a cross network learner, which will learn from this. And then the cross network executor, which does inference on the learned model. And finally, you can append columns and just visualize whatever you have. Okay, so let's start from scratch. Let's call this mnest, which is the dataset name, classification. Okay, cool. So first things first, we need to know how the dataset is set up. This is the dataset folder. It's split in training and testing separately because this is one of the standard datasets. So the same testing dataset should be the same to compare all the results from all the papers. The training and the testing have the same architecture. Basically, you have the label encoded in the folder name. So these folders, this is folder 4, where you will find all images as handwritten digits of 4. Similar to other labels, this is 7. And you will find so many variations of handwritten digits of the digit of the 7. Okay, so first things first, we need to really just list all these images and keep track of what the label is. This is what we are going to do now. We are searching for file, folder, something, list files and folders. And in here, we will give it the dataset location, it was in downloads. And it was, so there is JPEG version and PNG version. You can download them from GitHub or search on Google. I'm not sure if the JPEG version works on Linux, but we'll just give it a try. Important thing that we need to list all the files and we need to include the subfolders. Here we are taking inputs, we're taking training and validation. We just need to choose the training. We have 60,000 samples, 60,000 images. So we are going to run this. Now pay attention to what this is actually giving us. It's giving us rows of file names with the full path. All right, so here what we need to do is to check this subfolder name. If it is 0, then the label will be 0. If it is 1, the label will be 1, and so on. One thing to consider here, this is of type path, it's not of type string, so we cannot still operate on this. That's why we need to change this to a string, like so. It's giving it in something called location. Let's change this to something we can remember. I'll call it string path or something like this. Okay, cool. Now we can operate on this string, so we can create a rule, use the rule engine, and this one here you can specify what the rules are to label your um, paths or label your image files. So we want to check the S path, and we want to check from the string S path that is like a wildcard kind of format. So we want to match everything 0 and everything like this. And this will give us a label 0. Cool. Let's copy this and paste, 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 paste. Let's do weak editing here. There is definitely a better way to do this, especially that this folder architecture is called the ImageNet folder structure. So it is very common to find tools that already can pass this for you. But this is like a good practice on how to do this manually. 2, 3, 4, 5, 6, 7, 8, and 9. Okay, cool. So we'll call this our label. This is the new column that we will add. And let's run this. And here we see this is the path, the original path. This is the path converted to string, and this is our label in string. Okay, now everything that is in subdirectory 0 is labeled 0. Let's verify something at the bottom. 5 is giving 5. And 1 is given 1. We have 9 given 9. Okay, we are good. Now, next thing, we need to read our images, but this will take some time because it's reading them one by one. It's not really optimized for doing this. So we need to like sample from this or take a smaller subset of the data set. So we'll use raw sample here, and I'll just ask for like 5% of the data set for now. This is for demonstration purposes, really. Okay, so when we do this, then you will get some like these, which are cool. One thing I believe is that we need to check this one, stratified sampling over label, basically to get the same number of samples from each class, right? Now we have 5%. Now let's load our images. We want our images to be in a table so we can feed it to the neural network. So we need image table, something, image reader in a table, yes. There we go. And here we are reading from S path, yes, that's correct. And we're using the array image factory. I think the best, yes, this is in case you have channels in your images, if it is RGB, or maybe sometimes you have more channels than just RGB if you're adding transparency or if you are processing high spectral data from remote sensing satellites. And we are here creating a new table. Yeah, okay, let's have it a new table. That's cool. Now, if we read this, this will start loading the images one by one. And now you'll find your images here. These are your images. If you grab this into image reader, image viewer, sorry, and you just run it, then you open the view. It will give you the table like this, and this is the image viewer that they have here in KNIME. It's similar to the image viewers for medical imaging data, like MRI and CT scan, things like that. So it is kind of built on the same uh, structure or the same UI basics. Scrolling will give you zooming. Here will give you next image. I think here will give you next channel or next column of images, because remember, this is only one column of a table, so this table can have multiple images. In fact, let's actually do this and make an image calculator, because we need to normalize our data. So we want to get our image and divide it by 255.0, and we are not going to replace the image, we'll call it normalized. Okay, and let's check this, and this would be our new, so you can have a table of multiple images. One thing I forgot to fix is that being normalized is giving it unsigned by type. We need this to be double or float, because now we are dividing by 255. We want the values to be between 0 and 1. So when we do this, obviously this dynamic range is very small, 0 to 1, but this is from 0 to 255. That's why these are visible here and are not visible here. But if we grab this into a viewer and open that, you will find the same images that you were talking about. So these are the same images that you had the previous exact. In fact, you can swap between the two, and it should look exactly the same. The only difference here is that the second one, which is the normalized, I click the normalize here to visualize the pixel differences. So this one really just stretches the contrast of the image to be visible. My understanding is that the previous one is already stretched, so normalize here doesn't have any effect. Okay. Sweet. So now we have our data. We have our data normalized into between 0 and 1. Let's keep this here. For now, we might delete them later. Now, what else are we trying to do? What do we have in the table here? We have this one and we have this one. What is it that we are missing? We are missing the label, this, and we want to get this label to be one hot encoded. So with image reader here, can I just append instead of replacing something? Now when we play this, this will load, this will do, and let's see. So we have the path, S path, the label, the image, and the normalized image. Now let's take from this, because our label is now categorical, we need to make it numerical, so we will do a one hot encoding. We'll leave this for now, and let's work on our neural network to see why we need the one hot encoding. So let's do class input layer. This is our input layer, and this is supposed to be of the same size, 28, 28, and 1, because it on the deep learning frameworks require the channel. If the image does not have a channel, which means it's just a 2D image, the 28 by 28, you add a dummy dimension called, which is 1. This is of type float. A channel is last in class. In some other implementations, channel can be first. So just keep in mind to if things are not arranged properly, you're probably having a channel the channel location mismatched. Okay, and then let's apply this. My apologies for that. So we have an input layer. Now we'll drag from this and we'll add a convolutional layer like so. And if you double click on this, it will show you what the input is from the previous connected node. Now for this one, we want, let's say 3 by 3 kernel. The padding is valid. If the padding is same, then the size will not change. So it will keep 28 by 28 there. Now, the majority of our data points are between 0 and 1. So it makes sense to use sigmoid or 10H. I prefer to use 10H because it will give the filters the ability to have negative values, or the feature maps to have negative values, which can give more learning capacity to the filters. And as always, please name your layers. So call this mycomb1 like so. And we haven't named this one my input. So now if you drag from this and add another conv layer like so. Now this is taken from previous layer 26 by 26 by 1 because we use 3 by 3. There is an excess of 1 pixel at the very start and the very end of the image when you are doing the sliding window. So that's why this is it diminishes in size. So let's call this myconv2. And let's stick to 3 by 3. One thing we haven't changed before is that the filter size. So we'll ask for 16 filters. This means it will generate 16 feature maps. We'll keep it at 10. And here we need to ask for this for 16. Now, if you open this one, it will show you that we're getting 16 by 16, 26 by 26 by 16, because we ordered 16 filters from the previous one. Now let's do some pooling to reduce the dimensionality a little bit before we use the flattening and dense values and dense layers. So this is taking 24 by 24 again because of 3 by 3 we dropped 1 pixel from all the sides. Now the pool size is 2 by 2, and here we have to change this. By default in Keras or TensorFlow, it is already by default the same stripe, but here you have to specify it. So in pooling, you are really getting the maximum of all the pixels in the 2 by 2 window size, but you're also jumping with the window size with the same stride. So this is what makes it very effective in reducing dimensionality before we do the flattening. So here we can add flatten layer, which is going to change, which is taking 12 by 12 by 16, and we'll change it into a one-dimensional array. My flatten, and here we have, maybe let's do this 3 by 3 to drop it further. What do we have here? 8 by 8 by 60. Yeah, that's okay. That's close enough. I didn't give a name to this one. This is 1, 2, 3. So this would be myconv 3. Okay, cool. Now we need a dense layer, which is this one. And this one will get to specify number of neurons for the dense layer. So we'll treat this as our output layer. We have 10 classes, so we need 10 neurons, and we'll call this my output. And the activation function is, because this is a classification or multi-class classification, is going to be softmax, and this would be our model. So the image input goes into the Keras input layer, the image coming from the image calculator here, and the label is supposed to be at the very end. When we start training, you give it the input and the output. So we take from this and use Keras Network Learner. Here we need to give it training data and validation data. So we need from here to do partition, and let's choose 70% stratified to keep the balance in the labels. This is our training and this is our validation. And let's run this. It is failing because I don't think we have set the labels yet. Let's double click and see what do we have here. Okay, so first of all, we are feeding two images and this one's accepting only one image. So let's remove one of them. We'll keep the normalize and remove the other one. And that's in the input. The output though, it's not supposed to be an image. It's supposed to be of shape 10 because we have 10 neurons at the output here. So these are not valid inputs. That's number one. Number two is that we haven't actually prepared our labels yet. Our labels here are just string, and this one is expecting 10 values. So this is where we do the one hot encoding. So we'll do one to many. This is the node to do one hot encoding. And in this one, we will use only the label and we'll remove the S path. And that is it. If you check this one, you will find the label is 0. It will be 1 at column 0 and 0s everywhere else. If you scroll down quickly here, label is 9. It's 0s everywhere and 1 at the 9. And here, 2 0s everywhere, 1 at the 2. 0s everywhere and 1 at the 5. The main idea is that these are the 10 outputs that we want our neural network to learn here. So this is why our output layer is 10 neurons. Cool. And the main idea is that this this table, these values will be fed into the neural network learner, and these columns will be named to be the output, the desired output. The neural network, when it learns, it will not perfectly actually find the correct values, but because you're doing a softmax, and softmax will ensure that the sum of all of these would be always 1. This means the neural network will learn the distribution, give you a probability of how likely this label, this image, be associated with the label 0, because this value will go up. We'll see it when it works. Okay, so now we have one too many, and we'll do this with the partitioning. Let's just keep this tidy. So this is a one hot encoding done. Partitioning, we'll do this. Fantastic. And this is the training. Now here we get to choose the conversion. So we are converting it from double. Now it's excluded all the images and gave you the columns from 0 to 9. So we'll use these, and we'll use a loss function for binary for categorical cross entropy, because this is a multi-category or multi-class classification problem. Okay, so let's train this. We have still another problem. What do we have? Also, how do I get the log? It keeps saying open the log. Oh, I think it's here. No, no. Okay, execute failed. An error occurred during the training. Okay, it was deep learning network. I feel that I'm missing something. This is 28 by 28 by 1. Okay, channel lost. Okay. Okay. What am I missing here? Mm-hmm. Mm-hmm. 8 by 8 by 16, which end up 1024. We're doing this to 10. Should work. Um, we're taking two images, sorry. So let's do this. There we go. Come on. Yes. Okay, so our model has learned. Now we get to execute the model. So we do this and we only give it the validation data set here. In some cases, you might want to say duplicate this and split the validation into validation and testing like this. This is in some cases. In this case, you can just run the whole thing. It will keep pulling data from these connections. But this validation here would be very small. The testing data set here would be very small. We have actually an error here. Oh, okay. So the input is supposed to be an image. So we take only the normalized and we'll add an output. We want the softmax one. Yes. And this will be a number. And let's see what we have. So we have these values. We need to compare this with the label. So let's, do we get to append here? Let's go. No, doesn't look like it. Okay, cool. So what we can do is just join tables, column appender of this to this, and we'll see what we have here. So these are the original one-hot encoders. These are the predicted one-hot encoders. Let's call this predict. Okay, we'll keep it for now. And these are the two images that we have here. One of the things that we still need to do is to get the predicted value. So we need an argmax or a many to one. So to do the one-hot encoder, it was one to many. To do the one-hot decoding, it will be many to one, like this. And we will use the maximum. We'll get the maximum one out of this. And we are only interested in, oh, I pressed escape by mistake. Maximum. Well, I'm only interested in these. Oops. We are interested in the other ones, so we'll move these back. So from 0 all the way to 9. Now let's run this and let's give it a name. I think we call it a predicted. So these are the values, this is the label, and this is the predicted. Now let's give these some easier names to work with. So we'll call it one hot, predicted one hot. And we'll give it a dash here to be a prefix. And for this one, this is not important. This one is called predicted. Okay. And let's run these. So predicted one hot, these. Okay. We might need to filter some of these columns though, because it's becoming very crowded. Let's do column filter here. And we want to keep what? We will remove everything and we'll keep these. Let's take them in order though. So we'll keep the image and the normalized, put them here. We'll get the label to add it. Not sure if I can do this in order. It's okay. And then we'll get the predicted added here. And we'll keep these because we want to look at them. We can just get rid of these ones. And the path, the yes path. Yeah, well, hope this is the one. Now let's open these. We have the image, the normalized. This is the predicted one. And these are the predictions coming out of the neural network. Now keep in mind that this training, we haven't adjusted anything about the training yet. We only put the inputs and the outputs. Now let's do something about the training. First of all, we need more than one epoch. So let's do this as 10 epochs. And second, I prefer to use the Adam because it's easier to manage. So we'll start with this learning rate. We'll keep adding itself up. These are the parameters to control the momentum of the learning rate. The clip norm and clip value. Clip norm is to calculating the norm for all the filters of all the theta parameters that are learned and then clip them to 1, so keeps the values in check, closer or around 1, around the mean 0 and variance 1. Clip value is a more aggressive one, so this one will find any parameter that is above 1 and will just clip it to 1, or below -1 then clip it to 1. These two parameters are more used in deep reinforcement learning than normal classification and regression. If the problem is really complicated, you might have to resort to these aggressive measures, basically just to keep the network in check and avoid having the parameters exploding in large numbers. Okay, so we have 10 steps. We did Adam, and let's run the whole thing here again. There we go. Of course, this will be a little bit slower. That's why I chose 5% of the data set for the samples. Let's go. My guess is I can actually adjust the batch. The input batch size here is 100. What's the input batch size here? Yeah, still 100. Okay. How many samples do we have though? So this one, the training samples are 2100 and the validation is 100. After splitting the validation to validation test 630 and 270. Okay. So this one is finished. And let's see. Okay, so for images of label 0, we have a predicted of P1 hot 0. This is coming from many to 1 here. And these are the ones that are actually going to have the highest numbers or the highest probability that this class belongs to 0. Some of them are going to be exactly 1 with zeros everywhere, and some of them will be very close to 1 with minimal residuals everywhere if it looks a little bit like a 6 or a 5 or something, depending on what the features have there. Now if we go to the next one, this is 1, the label is 1, so we'll have zeros everywhere except for P1 hot, and this is 5, so 0 0 0 0 0, and then the highest value would be at P1 hot. This looks a little bit like a 3, for example, to the network. It sees some of the 3 features here. And you can go all the way to down here. We have 9, which is highest value at P1 hot 9. There is a confusion here with this one. It's misclassified as a 6, as a 4, which you can see it because of this empty space in the circle at the top. It can look like a 4. Okay. So one last thing before I close this video is let me wrap things up here with some annotation. So this would be the model, the NN model. Here, oops, no, yes, thank you, cool. And let's add another one for data preparation. This will be somewhere here, like this. We can actually have these two as train test split. So let's add another one here. Let's call it data split. And there we go. And let's just call it split. Yep. Now here, this is the learner and this is the executor. So let's add one here, learner. And there is inference. Like here. Okay. I hope you really enjoyed this one. And I'll see you in the next video when we do the an autoencoder. Okay, thank you very much and enjoy.